I'm going to start first with some of the questions you people asked. Hopefully, I will cover them throughout my presentation. Okay. Hopefully, I'll answer them as we go along. And so let me just state what the questions are. And it turns out that the questions that you folks asked are, I would say, almost 90% of what people ask out there as well. So it's like you hit them right on the nose. And you can see as soon as I put the questions here, you'll see why. The first one was, and they're not in any certain order, but I'll put them in an order in which I'm going to be addressing them. Okay. So the first one is Richard Feynman. He was a Nobel Prize winner in physics. Okay. Once remarked that he could not explain exactly why two magnets attract and repel. Right. We have two magnets. We don't know why what causes the mechanism, right? That's what we're asking, right? Could you tell us, that's your question, could you tell us why the current standard explanation does not work and how the rope hypothesis comes in? I'm going to be answering that question. What testable predictions, second question, does rope theory make? And to the extent that these predictions have been tested in practice, have they been borne out? So we will address that issue as well. Number three, there does not seem to be a way to explain how the ropes don't get tangled. Excellent question that people ask. Say, hold it, you got these gazillions of ropes out there in the world, right? Electromagnetic ropes, as we call them, that we're replacing the electromagnetic wave with, right? And people say, well, hold it, you got these ropes, you're talking about a physical entity, exactly. And they say, how is it that they don't get tangled? Perfect question. 99%, 150% of the people ask that question. Please define touch for us and show us how you would solve this problem. And the last one is also, do the ropes pass through each other? Okay. Those are standard questions. Everybody asks them. And hopefully I will address all those questions today, okay, in the presentation. So I want to give you a little presentation of what the problem is, where we have a problem today, especially in so-called science, in so-called mathematical physics, which styles itself as physics. And I'm going to say that mathematical physics, I'm going to argue here, mathematical physics has nothing at all to do with physics. Okay, so I want to put that right up front, okay? Now, let's start with some of the problems. And one of the big problems we have today is gravity. We have no idea what causes gravity. Here I have a little pencil. I hope you can all see this. Okay, here. Okay. We have a pencil. We let go of it and it falls downwards. Yeah, you don't believe me? Do it yourself. Okay. I think everybody has had something drop from their hands and it falls to the floor. Okay. All we need is one experiment in the last 10,000 years and we know something about gravity. Everything falls to the floor, right? What's the problem? The first problem is that not a single mathematical physicist, so-called physicist, not a single individual coming out of Cambridge or Harvard can explain to you how that happens, what causes it to happen. Okay? General relativity has irrational explanation. What's the irrational explanation? Why is it irrational? Well, because they say space-time is warped. Let's forget for a second space, because people think, well, space is maybe an object, a three-dimensional, blah, blah, blah. Forget about space. What they're telling you is time is warped. That's the explanation. And when you say time is warped, what does that even mean? What sense does that make? Okay, that's why it's an irrational one, because they're taking a concept called time and they're saying it's warped. And because it's warped, that's what prevents the Earth from flying out of the solar system, which is gravity. The Earth stuck to the sun, or the moon to the Earth. Why doesn't the moon fly out of the solar system? Because time is warped. They have this depression, a canvas that they illustrate, and they say the moon rolls around the Earth. It's like there's a wall there, and the moon can't fly out. And what you're staring at is warped time. That's why it's irrational. Quantum mechanics, what explanation do they have for gravity? Well, again, they work in the world of the small, right? And if you take that pencil and you let go of it, right, it falls to the floor, and they say, well, we should be able to answer that because we're talking about at least the world of here within Earth. And what's the explanation? First of all, they don't have really an explanation of gravity, but the one they give you out there that you will find is negative momentum transfer. That means that you send rocks out, right? You send all these rocks out, and instead of delivering push, they deliver pull. Okay, that's what negative momentum transfer means. It means you're sending some kind of particle out with negative momentum. When it hits you, instead of pushing you away, it drags you inward. That's only a mathematical I mean, you put a negative sign in the equation, you can get away with that. But get away with that in the lab. Try throwing
it's different. Yeah.
Attracted, or at the table, see if you're attracted. So we got a problem there because all these are irrational explanations. So you cannot explain, you cannot give a physical interpretation to gravity using equations, math, numbers, or whatever. That's the issue. Okay. And so the question is, how did we arrive here? And the answer is that the scientific method is screwed up. In short, I mean, that's the problem. For the last 400 years, since the days of the 17th century so-called scientific revolution, it's the mathematicians who took over physics and science. And they imposed on everybody on the world, in the world, they imposed on them their notion of what science is and what physics is. And what physics and science is, according to mathematical physics, is experiment, measurement, and an equation. Okay, so you do an experiment, you measure, and then you come up with an equation to describe what you just saw, and you publish. That's it. And so you ask them, well, what about the explanation? What is the cause? What is the explanation? Oh, that's not part of science. That's not part of physics. That's philosophy. And you say, oh, I thought that was physics. And so that's where we have our first problem. We have a clash against what we have today, that that science and physics is all about experiments, measurement, and equations. And so if you ask, why don't we have rational explanations? Because those are not part of science. Those are considered part of philosophy of physics, philosophy of science, or whatever. But they're not part of what they call science or physics. And so these people give you a physical interpretation, an irrational one. And when you receive that, you say, well, that doesn't sound very rational. Yeah, we don't care because that's philosophy. That's the answer. That's what we have today. Okay. Today, we're going to talk about something else. We're going to talk about real physics. We're going to try to give you an explanation of how this happens. Okay. How gravity actually works, which is totally different than what these people have suggested for the last 400 years. And the other issue here is that, the types of what we have for science, what these people say is science, which is measurement, equations, etc., predictions, observation, none of that helps answer the question that we're asking. We're asking, I want to know what causes this to fall to the floor. That's how simple it is. And they're saying, well, we do observation, we do measurement, we can tell you how fast it falls. Here's the equation, but you're not telling me why. And that's when they dismiss it and say, well, that's part of philosophy. So the questions we're asking are not being answered because science is not, or the way it is defined today, is not designed to answer those types of questions. That's the root of the problem, okay? So I want to just clarify that up front, okay? Okay, so what's the issue? Let me give you a scenario here, okay? And I hope you can picture this in your mind. You're here with your friend, okay? And you look out at the distance and you see a fellow, maybe a farmer, right? Pulling on a rope. And at the other end of the rope, there's a donkey or a horse. Very simple scenario. So this guy's going like this, pulling on a rope, and the horse or the donkey comes towards him. And so your friend asks you, how did the donkey move towards the farmer? How did that happen? It's very simple. 5-year-old can answer that question. The guy pulled on the rope and the donkey came closer to him because he's tied to the rope. It's all physically connected. No problem there. We all understand that. Same scenario, same exact scenario, but you can't see the rope. Okay? So you see a farmer going like that, maybe because there's too much light in the background, so the rope blends in with the background for whatever reason. Maybe your eyesight is not good. I don't know. The question is, you see the guy going like that, and the donkey comes towards the farmer. Now your friend asks you, how did the donkey come closer to the farmer? And you say, oh, we'll never figure it out. We need to run more tests. I need to run an experiment. We'll never, maybe sometime in the future we'll figure it out. And the only difference in between scenario A and scenario B is that here you can see the rope, the mediator, and here you cannot. That was the only difference. Okay, so we're getting to the problem. The problem is that people say, well, if I can't see it or touch it, it's not there. And there we have the difference between objective and subjective, which no one has defined, by the way, in the last 10,000 years. Objective is what comes out of the scene, out of the phenomena. That's what comes out. That's what's in there for real, whether you can see it or not. Subjective is what you can see, hear, taste, smell. That's all subjective. And so if you can't see it or touch it, people say, well, it's not there. Well, not true. It could be there. That's subjective, whether it's there or not. Whether you can see or touch it, that's subjective. Okay, and so we need to distinguish what is objective from subjective. And here I'm defining it. I'm saying objective is what comes out of the scene, whether you can see it or not, or touch it or whatever. Okay, so that's the issue. And so we have this issue where the mathematicians have used the term action at a distance. So when they see the farmer moving his hands like that and the donkey moving towards him, but they can't see the rope, they say, oh, it's action at a distance. Well, action at a distance is an explanation, a so-called scientific version of black magic, of witchcraft. They're saying it just happens. You haven't explained anything. Did God do it? I mean, how did that happen? And what they're saying is, it's action at a distance, meaning we don't know. We didn't see it happen. We can't experiment on it. What are you going to experiment here? You can't see anything above it. You can't see anything below it. Something is in contact with this pencil, and otherwise it wouldn't fall to the floor. And you say, well, is that true? Are you saying that something really came in contact, but I can't see it or touch it? And so the issue here is that, you go to what is an object? What is a thing? Because if you say that nothing came in contact with a pencil, you're doing black magic. You're doing action at a distance. You're doing, witchcraft. But we have to assume that if we're going to explain this rationally, that there is something in contact with a pencil, either something pushing or something pulling from below. That's why this falls to the ground. Otherwise, we're doing black magic. We're saying action at a distance, which is the scientific version of witchcraft, okay? And this takes us to the issue of what is an object? What is a thing? No one has defined the term in the last 10,000 years. What is a thing? And people say, well, it's that which you can see or touch. That's the general notion that people have. Well, we can't see the air. The air is made out of atoms, no different than your chair. You can see the chair and say, okay, that's a thing. But the air, it's not a thing because I can't see it. It's made out of atoms. It's just loose atoms. But air is a thing. I breathe it. I take it in. I see. I move my hand and I touch something there. And how about touch? Well, touch. I can't touch the chair on the other side of the planet. Do I have to go and touch the chair for the chair to become an object? Or was it an object before I touched it? And so the problem is the definition, the notion we have of what an object is, what a thing is. A thing is not that which you can see or touch, which is our normal notion of objects. A thing is that which has shape. All objects in the universe have shape. If you can think of one that's not an object that does not have shape, please let me know. Okay, any exception to the rule? It's a universal criteria. In other words, every object has shape, and that's the definition of the word object. That doesn't mean that you can see or touch it, especially anything that is subatomic, below the atom. Okay, we can't even see it, let alone touch anything below that. So the issue here is that we had a wrong definition or a wrong notion of what an object is. And here we're saying that here's an object, something here, right, or above, that is in contact with a pencil that we cannot see or touch, but it's a thing because it has shape. It's a shape that we cannot see or touch. Once we make that assumption, it changes the whole picture. Now we're in a different ballgame. Now we're no longer in this magical realm of mathematical physics or whatever. So we had to distinguish what an object is. That's bottom line. And the only word you will not find defined in any textbook of physics today, and I challenge you to do this, go out there and look for any textbook of physics, see if you can find the word object defined. You would think that the first word they would define in the textbook is the word object, because you can't do physics without an object. If you remove all objects in the universe, all atoms, everything, so that you have absolutely nothing, what's happening? Well, what are you seeing? What's taking place? What phenomenon is occurring? No, you have to have objects, and no one ever defined the word object. And everybody has this loose notion that it's that which we can see or touch. And that was the wrong definition or the wrong notion. No, an object is that which has shape. Not all objects can be seen or touched. We do not run an experiment to prove the existence of a chair and say, oh, now it is an object because I can finally touch it. No, it was an object before you touched it. And besides, touching or seeing requires two objects, the one doing the seeing or the touching. So it's an irrational definition or irrational notion to apply to the word object in a scientific context. Once we have that settled, now we're in a different ballgame, like I'm saying. Now we're going to be talking about real objects. And the objects we propose for gravity is a rope-like entity. Now, what do we mean by people say, well, it's a rope, it's made out of atoms? No. We're talking about the subatomic world. So this is not made out of atoms. We're saying that whatever entity is there, very thin, extremely thin, unimaginably thin thing, looks like a DNA-like rope. It looks like this, two twined threads. That's what it is. And light consists of a torsion of this rope. Torsion, it's the fastest thing known to man. Nothing is faster than torsion, because it doesn't go anywhere. You put the rope, your grandmother's rope, where she hangs her clothes, right, across two poles, and you put two clothespins at each end. You move one, the other one moves instantaneously. Why? Because nothing went anywhere. They just twirled in place. And the only thing that essentially moved was a signal along the rope. It propagated along the rope. And so that's when you find out that a torsion wave is much faster than a transverse wave or a longitudinal wave. Longitudinal wave, for example, sound, and transverse waves is what they always thought was light. But see, those are all one way. The torsion wave travels in both directions simultaneously. Okay, goes from your eye to mine and mine to yours at the same time. We're both receiving a signal constantly. So not only are we saying that light is a torsion of a DNA-like entity that's between any two atoms, but now we can explain gravity because we have a physical connection from atom to atom. And if you look at number one there, the Muller pull, you see that there, Ed?
Yeah.
Maybe you can put that up there. Okay, and let's see if we can read this. Let me see if I can read it because it's kind of small, unfortunately, but here, let me read it for anyone who needs to know what this is saying. This is what Richard Muller says. He's from the UC Berkeley. Okay, so he says, for example, if you have the Earth, there's a big mass here, and you have you with your little mass here. Every atom on the Earth is pulling on every atom of you. You're also pulling on it. The amazing thing about gravity is that it goes right through things. So what is he saying? He's saying, look, every atom on Earth is pulling on every atom of you, and you're pulling on it. I mean, I think it's straightforward what he's saying. I'm not sure if anyone missed anything there. gravity is a force of pull of some kind. You have to have a mediator between the pencil and the earth. And what we're saying is that every atom that makes up this pencil is tied to every atom on earth. Okay? And people say, I can't see it, I can taste it, I can't smell it. Yeah, I know. You will not be able to see, smell, taste it because it's an invisible, intangible entity. And therefore, now we answer one of the first questions there. There's no test, no experiment you can run for something that is invisible and intangible. Because when you go to the lab, what you're going to be testing, essentially experimenting on, is invisibility and intangibility. You're going to use your hand and your eyes. And we're saying that you can't use your hand or your eyes for an intangible, invisible entity, like we're suggesting that connects any two atoms. But here you have Miller saying every atom on Earth is pulling on every atom of you. You're pulling on every atom of it. How do you explain it? How do you illustrate that unless you put some kind of connection between every atom in the universe, every atom of you to every atom on Earth? Okay, so that's what we're saying. That's what's happening. And now we can see the mechanism. If you go to number 3, I think it's number 3. Yeah, number 3, it'll show you why a spoon falls to the floor. That every atom from the spoon is connected to every atom on Earth. As it falls, the ropes in this case, right? Every atom is connected to other atom on Earth with ropes, right? Electromagnetic ropes, very thin, very invisible, very untouchable ropes, right? And what's happening as it falls, the ropes fan out. So if you take them to the infinity, all the ropes come together, and it's like a single rope, like a single coaxial. But as they come closer to the object, in this case, the Earth, they all fan out, and each one acts individually. And so that's why you have the acceleration of gravity, because you have more and more ropes working or acting individually. That's the mechanism that we're proposing, okay? And so we have a physical mechanism of why explains the acceleration of gravity. Okay, that's the point here. And so, yeah, we have this. And then people ask, well, hold it, you have all these ropes in the universe, and again people say, how come they don't get tangled? Again, looking at C-touch, people have this in the back of their mind, they can't get away from that, and no problem. The first issue is that in quantum mechanics, at least, they don't treat the subject in general relativity, but in quantum mechanics, what you have is the same thing. You have what is known as superposition, and what they have, superposition of states, because they're going to talk about math. They're not going to talk about physics. They're not going to put objects in there. They're going to say, well, we have the wave and it has so much vibration of the field. They're going to be talking about numbers. But what they're saying essentially in a roundabout way is two particles can occupy the same place at the same time. And there, I think if you look at number 07 there, where I pulled out some quotes from so-called physicists or people who are into physics. Those quotes come out of Quora, the next, that one there. I don't know if you can read all that. Let's see if I can read them for you. Give me a second here. Let me get it up there. Okay, first one says, the answer is yes. Two electrons can occupy the same position. They have to be in different states, though, because of the Pauli exclusion principle. That's out of a PhD student in theoretical physics. Another one, a quantum physicist, says, in a multi-particle equation, it treats several particles as being in the same place. And then you have quantum, that's a quantum physicist. And then another PhD in electrical engineering says, it's more correct to say that the particle has no position. So they give you the runaround, but they're saying the same thing. They're saying that according to quantum mechanics, superposition says that two particles can occupy the same place, the same space, the same position. And even worse, they say that one particle can be at two places at the same time. It's like nobody questions that. But when it comes to the rope, people say, how come they don't tangle? Well, it's the same question. They're saying that a single piece of the rope, occupies the same position, place, space as another rope. And you say, how can that possibly be? Well, why didn't you ask the question with quantum mechanics? I mean, there everybody accepts and say, oh, yeah, that's obvious, right? It's okay. No. You first ask the question in quantum mechanics before you ask me the question. So that's the first answer, okay? But we have a better answer than that. And again, it's that definition of the word object has nothing to do with see or touch. In the subatomic world, we're saying the same thing as quantum mechanics. Objects can be at the same place at the same time. We don't say the opposite of what quantum mechanics says, that one object can be at two places at once, which is to us is irrational. But we do agree with quantum that two objects can be at the same place at the same time. So now we get into the question of touch. You know, before I can cut across, a rope can cross another one, it has to touch. Then you can cut across or tangle, right? Because something stops it. But before you can get to that point, you have to touch it. Two things have to touch. The scissor has to touch the paper before you cut it, okay? So the question is, what does the word touch mean? And again, no one in the last 10,000 years defined the word touch, so important for the purposes of physics. And so what are we saying? We're saying, look, touch is when two objects become one, when there's no space between two objects. As long as there's space between two objects, you haven't touched it. Like, you know, I have two fingers here, right? I press as hard as I can, or against the table. And it turns out that, you know, there's always space in between the two fingers. So the fingers have not touched. In the 3D macro world of ours, there is no such thing as touch because there's always space in between any two atoms. They don't blend to form one atom. Or when they do, then you can say that you have touch. But in normal everyday things, we have no such thing as touch. But people say, oh, you touched your finger. No, I didn't, because there's space in between. The only way you can define touch in irrational, that you can use it in a rational manner, is if there's no space between two objects, meaning that two objects have become one. There's no space, empty space, you know, between them already. Okay? And so the question is, you know, in the microscopic world, in the subatomic world, the rope has the ability to go through because it doesn't have the property of touch. Okay? That's an assumption. It's the same assumption quantum makes with particles. So please don't hold it against theory, okay? I mean, if you're going to hit the theory with touch, hit first quantum mechanics. Okay? Don't come to me and tell me, oh, quantum mechanics can explain it. No, they cannot, okay? Okay, so all I can say is first, the reason this pencil falls to the floor is because every atom of this pencil is tied to every atom on Earth. You cannot explain it what is push gravity, which is particles pushing the pencil, because the pencil on the other side of the planet is falling also towards the center of the planet, you know, the one in China. And what the particles over there are pushing it in against mine, you know, why? You would have to explain that. You would say, why do the particles here push it that direction? The particles on the other side of the universe push it, or the Earth push it in the opposite direction. And you cannot explain that. The only way you can explain this is if every atom of the pencil, like Mr. Richard Muller said, is tied to every atom on Earth. As it falls, the distance between the Earth and the pencil becomes shorter and shorter and shorter. The ropes fan out, and you have the acceleration of gravity. Now we have a rational explanation, at least, for this. Whether you believe it or not is a separate issue. We have an explanation. That's all I'm saying. And as far as the rope for light, we have an explanation of what light is. We're saying it's a torsion along the rope, meaning that every atom is connected. You know, like if my fists here are considered the atoms, and you have the rope in between, tight, being pulled tight, and you have a torsion moving from atom to atom. Now we can explain light, why it's so fast. We can say, look, we have the grand unified theory, because in one mechanism, we can explain both gravity and light, which is what they've been looking at for so many hundreds of years now.
All right, I have a quick question, Bill. So, like, suppose
we're up for questions.
All right, so suppose I get out of this planet and I'm just floating out into space. Let's just say my body does so like forever, incessantly. Will the rope never break? The rope will just be infinitely elastic?
Okay, Ed, let me just a little piece here that maybe I should clarify, which is important to clarify. Give me a second here. We're saying that all there is in the universe, according to quantum mechanics and according to general relativity, string theory, essentially all of these mathematical physics, their assumption, their bottom line assumption is that everything is just particles, discrete particles. And so they have this particle moving in that direction, the other one in the other direction. All they talk about is particles. Particles being created from the vacuum, particles that came into being from the Big Bang out of nothing. They cannot explain that either. They say that's an unscientific question. We're saying that this is all there is in the universe. There's a single closed loop thread, like a rubber band here that you can see, right? This thread turns into every atom connected to every other atom through an electromagnetic rope made out of the same single thread, twine thread, and it goes into making the atom, which the atom itself is made out of those threads, continuing to another rope, to continuing to another atom, another rope, another atom, and so on down the line. So if we were to untangle every atom in the universe and every rope in the universe, we would end up with a single closed loop thread. We're saying this is the assumption. We're saying this is all that really exists ultimately in the universe, this floating in space. This has turned into every atom connected to every rope, connected to every atom, connected to every rope. So now you ask, does the thread essentially disintegrate? It doesn't. That single thread is untouchable. It can't touch itself. It kind of winds around itself, forms the atoms, and you have the property known as touch, or, essentially colliding, the fact that you have some kind of ball there is with the atom and above. Anything below the atom has no property to touch. And you can't break it either. This is something terrible that you can tear, right? That's what.
All right, and then your explanation as to how come ropes built tangles that they actually can pass each other and occupy the same location, and they're able to do that because
exactly. And one of the issues here that people have a lot of trouble with that, because they're saying, how can that possibly be?
It's like a ghost.
It's been telling them for the last 100 years the same exact thing. Two particles can be at the same place at the same time, as long as they have what is known as a different state, a different vibration state, so to speak. So they're saying the same thing as I am. I mean, we have no difference in that sense. We're saying the subatomic world works a little different. And what we're saying is you can't use the word touch in the subatomic world. That's bottom line.
Okay, and so in the micro level world, since the ropes belong in that category, their properties are just intrinsically different, so that the ropes can pass through each other, and that's why ropes out here can't pass through each other.
Not only that, let me add to that a little more. The thread, the single thread as we call it, has properties that we see today in gases, liquids, and solids. This magical thread, Wonder Woman's rope, lasso, right? It has properties that include solids, liquids, and gases. In other words, it inherently has these properties. That's why the thread is able to mimic all these properties in our macro world of atoms, okay? But yeah, so in answer to your question, yes. And in addition to, we have the fact that the rope has this versatility, that in the subatomic world, it has these strange properties that we can only make an assumption of. You have to make an assumption at some point and say, well, what if, right? So you make a supposition and you say, let us assume that Mother Nature has this single thread out there. This is what it is. And this turns into all these atoms, ropes, etc. But they don't have the ability to touch unless they are atom or above. Once you get into the atomic world, then yes, now you have the ability to touch, what we call touch, or actually collision, because you're really not blending them. You're not eliminating space between the atoms, because otherwise they wouldn't be single atoms, right? But other than that, you don't have touch below the atomic level, and you start having this so-called touch property after the atom is formed. Now you can collide things. Other
Yeah,
than that, you
that's
can
what I'm
collide.
having a hard time understanding because it's like so the small ropes in the micro universe can, but the ropes, excuse me, got a cough, in the macro universe can. And and everything's made out of the electromagnetic ropes in the micro and macro world. So how come the ones in
Right.
the macro world can touch?
Yeah, because why? Because now you have a volume. You've made a ball, which is the atom. The atom is not this Bohr's atom, Niels Bohr atom, which is a proton, which is orbited by an electron bead. That's not our atom. Our atom, in fact, I think I have it there. No, I didn't send you the atom, but you can see. How can I show you this? Essentially the rope turns into each one of the threads of the rope turns into the electron shell. So the atom is really a ball, which is the shell, which encapsulates. You can imagine it as a star. All these single threads coming out of that, gazillions of them, and they're encapsulated by what we call the electron shell. And what these people have always looked at when they say, look, I saw an electron bead, right here, what they're looking at is a location on the electron shell or electron membrane, electron balloon. It's a balloon that is encapsulating a star. So it's a different model altogether. I do have in the videos that I have in my channel, you'll see that there. So you just got to look at that over there. But my point here is that we have a different atom. It's not this electron bead that orbits or is somewhere around the proton ball, bowling ball, right? It's a totally different model. And again, one of the things that quantum has never been able to explain, and which was the reason why quantum came into being in the first place, is they could not explain why the electron, which is a negative particle, and why doesn't it fall to the positive proton if positive attracts negative? And to this day, they cannot explain the mechanism of why the electron stops at a certain point and then just keeps being around the proton ball. Why doesn't it fall directly into the ball? Or why doesn't it spontaneously fly away? They cannot explain either one. They've never explained that, and that was the reason they went into quantum mechanics. So to this day, we have no explanation for that.
So when there's so many ropes just together in a mass, there's so many of them, because that's what you mean by volume. That's what makes it able to be touched.
No. The rope is not able to be touched. It's the atom that is, for the first time, the smallest entity that has a property of touch or of collision.
So let's just go to the micro universe. So atoms in the micro universe can touch. Just the ropes between them can't.
Correct.
Oh, okay, I get it now. All right, but
because you created a ball, with the threads. Remember, we're talking about threads. We should not confuse rope with threads with ropes. There's always a difference. Thread is, what makes up the rope and what makes up the atom. And we're saying the thread can go right through the thread because it doesn't have the property of touch. The property of touch is an emergent property that occurs when you have this ball, this volume called an atom, hydrogen atom being the smallest one, right? And that's for the first time that you have not the ability to touch really, but the ability to bang and collide. This is the proposal.
Okay. But isn't an atom just made out of ropes, or is it ropes and something else?
Threads, please, threads. Okay, we got to keep those separate. People get them confused, and
ropes connect.
No problem, but I just want to clarify that.
The threads. Okay, atoms are made out of threads, but the ropes connect the atoms.
Correct. And the question is, if you have two atoms, then you have this situation where you have two balls, right? And let's assume this is a helium atom, which is bigger than the hydrogen atom, right? And they have the ability to hit each other, to collide. They can't occupy the same space. They cannot really go through each other unless you go under certain circumstances, which is beyond the scope of this talk here today. But they collide for the first time, because now you have a volume of all these threads that are making up these two spheres. Okay, so that's when the ability to touch comes into play. But when you have this, when you have just a thread, well, I hope you can see it. Then this one doesn't have the ability to prevent another thread, like for example here, right, to go through each other. They just go. It doesn't have an ability to stop it. Okay, that's the assumption that we're making. We make these assumptions in order to understand the theories founded upon that. And yeah, what happens in the subatomic world is a little different than what happens in the macro world of atoms and above. And quantum has already verified a lot of that stuff. So we're not too far away from what quantum is proposing.
Okay, and so the reason the ropes don't touch is just because of the intrinsic property of the rope?
Of the thread.
Of the thread.
Yeah, for that matter, the rope itself. Okay.
Just
yeah, it doesn't have the ability under certain circumstances, because now you asked the question about magnetism, right? Here we have two magnets. Okay. I hope you can see them here.
Yeah.
Okay. And these are magnets from the refrigerator. Okay. And you see those two dark circles, those are magnets, right? And you can see how they attach each other. And so the first question that we have is there nothing here? And people say, well, I can't see anything. I can't touch anything. So there's nothing there. No, that's not the definition of anything, of something, of object, of thing. No, the definition of thing is a shape. There's something there that has shape. Now, it doesn't have the ability to see and touch by humans. Okay, but obviously this magnet recognizes something in there because it's acting upon it. Okay, so how does this magic work? And so if you look there, the one that you have there right now, it shows is that, let's see if I can explain with my hands. Well, let me show you with my hands. Let's explain first, because we all are acquainted with north and south, right, of a magnet. And just imagine ropes, two guys skipping ropes, right? There's two guys in parallel skipping ropes. Now the ropes, let's assume they go against each other. So they're facing each other. They're both skipping ropes. The ropes are banging against each other. It pushes them away, okay? Because it goes like this. Now we turn one of them 180 degrees, like we do with a magnet. Now we're going to say instead of north-north, it's going to be north-south. So we turn it around 180 degrees. Now they're both going like this, okay? You got that so far?
Yeah.
So now when one comes down, the other one comes up, and now you have attraction. So here you had repulsion, and here you have attraction. One coming down, the other one getting to it, touching it and pulling. And so now we have the mechanism of what's between those two magnets. We're saying if the threads, not ropes, but threads, gazillions of threads swinging in one direction and the other one swinging in the same direction, they attract. And if they swing in the opposite direction, when you turn the magnet around 180 degrees, now they push each other away. So we have attraction and repulsion with one mechanism. They're essentially the swinging of threads. And so now we have an explanation, finally, a physical interpretation. Now, whether you believe or not, that's a separate issue. We're just giving you a mechanism that you can, sink your teeth into.
Gotcha. All righty. Well, thanks for that presentation. And before we move on, so you also get Bill Gates' book, his magnum opus that was published in 1999. He's done 4 editions of it called Why God Doesn't Exist. You should just, you can get his email on his website and just give him $40 via PayPal, and he'll send you a copy like you didn't mind. It's a good book. It's like about 500 pages long. It has everything he teaches about physics and his online videos in here. So yeah, I highly suggest reading it. Alrighty, and then Keith, did you have any questions for Bill?
Yeah, I can think of 3 things. I have like a relatively simple question, and then I have like kind of a hard question. So
let's go with the simple ones. I don't like hard questions.
In terms of like, what can your theory account for something? That's all. The simple one is, how does it differ from string theory, right? Because
Okay, let me answer that because a lot of people have that. They say, oh, string, rope, it's all the same thing. No, you keep in mind two things. The first one is string theory is a mathematical, it's not even a theory. Mathematics doesn't have any theory. Mathematics is just description. Descriptions are not theories. An explanation is a theory. When you explain something, then you have a theory. And all the explanation from mathematical physics, where they go, whether you bring them from general relativity, quantum mechanics, or string theory, are all mathematical descriptions, and not one of them is a rational theory. It's not rational because they're using concepts as physical objects. They say the field, energy, mass, all those are mathematical concepts. Time, those are mathematical concepts. So that's the first issue. The second issue is that if you look at string theory, all they're saying is that what is a particle? So they're like trying to justify quantum mechanics, which is a particle theory. And they say, what is a particle? Well, a particle is really they call it a string, but it's not even a string. That's misleading as well. What they're talking about is one-dimensional line, a mathematical concept. A one-dimensional line has nothing to do with physics. It's got to do something with this notion that they had of geometry, that a point is a zero-dimensional nothing, just location. And what is a line? Line is a one-dimensional whatever, because there's no such monster as a one-dimensional anything that we can even imagine. So what they take is they take that one-dimensional line, not string, and they tie it and they make a circle with it, and they say, oh, we have a particle. Because now that single one-dimensional line is vibrating, and that's what a particle is. So it's got nothing at all to do with the rope model that we're presenting. Theirs is a mathematical theory, really not even a theory. It's not theory, it's just mathematics description. And ours is a physical explanation for how the universe works. So we have big difference there, big dividing line. So that's the first answer to your question. And the next one, what was it? Give me the hard one now.
All right. So you say that time is not what, say, general or special relativity says it is. So one of the reasons that people sort of don't question it is because it makes certain predictions, like, for example, that the closer you are to a large source of gravity, like the Earth or a black hole, or the closer you get to the speed of light, time slows down. And so we put satellites in orbit, and we notice that their clocks are different than the ones on Earth. That seems to confirm what general relativity says, but
okay, very good.
I think he's dealt with that.
You fellows are asking the exact questions that most people have, in their back of their mind. So you're raising the exact questions everybody asks. And so the first thing we have to say here is, in physics, we have no use for time whatsoever. And people roll their eyes and say, oh, Bill, what are you saying here? What do you mean we've been dealing with time since the days of Newton? No, in physics, we have no use for time. Let me tell you why. Because physics is about physical interpretations, about mechanisms, about causes. Time has to do with description. I want to know how much time it took the lion to catch the deer. I put the stopwatch and I say, it took 30 seconds. Okay, so far I only have a description. Time can only be used to describe. I cannot explain anything with time other than general relativity, where they say, well, warp time is gravity. That's the explanation they give. But time can only be a measurement of something. Okay, and I can measure how fast something runs, how long it took something to happen. Okay, that's the first issue. But then here we have the problem with experiments. Okay, we have no use for experiments in science either. Roll of eyes. Oh, Bill, what are you saying here? We have redefined science. We have redefined physics. We're saying that experiments have nothing to do with physics. You can do all the experiments you want in your lab. You can get in your dark basement, do all the experiments you want. When you come to the conference, we want you to explain. And you say, well, let me do the experiment for you. No, don't do the experiment. I don't care about your stupid experiment. I want to see what your explanation is for the experiment. In science, we explain the experiments, not do them. You can do a lot of experiments, not learn anything from them, or get the wrong conclusion. So you can do experiments like gravity probe B or GPS, right? You have GPS out there and they say, oh, it works. Yeah, it's like Thomas Alva Edison said, I have not failed. I just found 10,000 ways that don't work. What he was saying is he tried one thing after another until it worked, until he got his filling for his light bulb. And technology is like that. GPS was developed through trial and error. They sent gravity probe A first, then later on, a few years later, gravity probe B. They measured and they say, okay, here the satellites or the what is it? The nuclear, the atomic clocks ran at a certain speed and here at another speed. So they knew that. They knew that for trial and error. They set one up and they said, okay, this is the speed here and this is the speed here. This is how fast it goes here. This is how fast it goes here. So they do all these experiments and they can do GPS. Does GPS prove that time is warped? That there is such a thing as time that is curved? Hopefully not. Just like, quantum does not, a computer does not prove that that a particle can be at two places at once in quantum. Okay, just the fact that the computer works doesn't mean that they proved what their theory is, which is a particle can be at two places at once. And this is the same thing with everything. Technology does not prove a theory. Okay, this is a big error, this big misconception that people have out there. No, the fact that GPS works and the fact that they were able to measure all these things, it's just a description. We still don't have an explanation why the moon doesn't fly out of the solar system. They don't have an explanation for why this pencil falls to the floor. And you say, hold it, we have all these satellites and we run all these experiments, all these things, and they cannot explain a single simple experiment like a spoon or a pen falling to the floor. So the fact that we use the word time and that they play around with it so much, aside from the fact that they never defined it, you can look up the definition of time, you'll go nuts. You won't find a definition. Time is what a clock measures. What is that? I mean, they don't have a definition for the word time, but they use the word time to explain, and they say, oh, we know everything about time because, look, we have GPS and all this other stuff out there. No, we have to be, what is your explanation? What is the cause of gravity? Why does one clock run slower than the other or faster than the other? And I always give the experiment here. Let me show you. This is known as a clock, okay? Known as a sand clock or an hourglass, right? And you turn it around and all the grains start falling to the other side, right? This is a gravitational clock. If you're going to check time against gravity, this is the clock, okay? And let me give you an experiment that you can do and prove Einstein wrong. Einstein said if you take the clock farther out into space, right, it'll run, It'll run slower, and I'm sorry, it'll run faster, and the one close to the Earth runs slower, right? And that's not true. I take this clock, my clock, right, not an atomic clock, an irrational and inadequate clock like an atomic clock. I'll take this one. And this one runs faster closer to the center of the Earth than if you take it out into outer space. And that destroys Einstein's assumption for, gravity, which is that clocks should run at a certain speed out there and at a slower rate at the Earth. So they're saying that, if you're at the top of, the Eiffel Tower, your clock is going to run at a different speed than the one at the bottom of the tower. But yeah, the one at the bottom of the tower, if you do an atomic clock, will run at a different rate than if you use one of these guys. And so which clock should we use? I mean, this is a gravitational clock. And if you don't believe that one, you have this other one, like the time dilation thing that they talk about, that you have two twins, one leaves to go to the black hole and come back. And after many years, he's only experienced, according to his clock that traveled with him, he's only experienced 5 years, and the guys on Earth experienced 50 years, for example, right? Well, this is very simple, very, very simple. How many times did the Earth go around the sun? That's the definition of a year. And so the Earth went around the sun 50 times or 5 times. It could have been both. And when this guy comes back, hopefully the Earth went around 50 times, as the guy on Earth said, and not as his clock said, counting seconds while traveling. So it's all nonsense, mathematical nonsense, which they introduce into physics as a done deal. This is where the problem comes in. So the issue with time, we have to be very careful. First, the word time has never been defined, and it will never be defined by a mathematical physicist, because it's not, they're not into definitions. That's primarily the reason. But then they don't care about the definition of time, because what they're going to be using is seconds, and they're going to count how many years you are, how many candles you got on your cake by putting seconds in there. So they put 1 candle for every second that you live. They say, this is how many seconds you've got. I don't care about seconds. I want to know how many times the Earth went around the sun. That's physics. You can't have it both ways. You can't say, well, my clock measures such and such things, so many years. I don't know how many years your clock measured in seconds and you were moving. I know how many times the Earth went around the sun, and that's going to be the definition of the word year. That's how many years I have. So it's very simple. And then again, they don't have definition for the word time. That's the first one. Then they use time. If they want to use it in their equations, seconds, minutes, no problem. But don't bring them into the world of physics. Don't tell me you can explain something by saying that I'm going to bend time, warp time, or that gravity bends time, or some nonsense like that. That's not physics. That's irrationality completely.
Anything else, Keith? Are you done?
He seems less not the opposite of enamored, less conflicted about quantum mechanics than relativity. So I wonder if his rope theory has an explanation for, or if it's any different than what's called quantum entanglement. So you take 2 particles and move them apart, and you change one property, and the opposite property appears, even if it's way like in a million light years away, instantaneously with no speed of light.
Distance. Yeah, they call it action at a distance, which we said a minute ago. What was it? Witchcraft? Black magic? I mean, if I have 2 particles here, right? Here we have 2 particles, right? And they're separated. We can say it's a million years. It doesn't matter. They could be just that far away. No problem. What these people are saying is this one moves like clockwise or counterclockwise, right? And then instantly, like no time, 0 time, this one moves. For example, this one moves clockwise, this one moves counterclockwise, or vice versa, right? That's what they're saying. They're saying there's no mediator. We have a problem there because they're saying there's nothing in between them. Why is there nothing in between them? Because they say we can't see or touch anything through our experiments. Why can't you? Well, you got the wrong definition of thing. A thing is not that which you can see or touch, it's that which has shape. And this thing that's there has shape, but you cannot see or touch it. That's the first issue. The second issue is that hopefully there's something between these 2 things, because otherwise we're all crazy. We're doing black magic. We're doing action at a distance. Okay. So if this changes instantaneously, well, we can do it with a rope. And here you can see it very clearly. And we'll do it this way. Okay. I want you to tell me, I'm going to twist the rope, right? And how is the rope twisting according to your eyes? Tell me, is it counterclockwise or counterclockwise?
Clockwise.
How is it?
Clockwise.
So over on my side, it's counterclockwise. So strange. Okay, let's turn it the other way around. How's it twisting now for you?
Counterclockwise.
It's clockwise. So we have instantaneous clockwise and counterclockwise, which is what these people cannot explain. Light. Light, that's the photon turning clockwise, counterclockwise at 2 separate points where they measure. That's what's happening.
Okay, so what happens when you turn on a flashlight according to the rope hypothesis? And the beam, you see the beam.
Good question, Ed. Perfect question. We have to, let's start at the assumption. The assumption is that all atoms of your flashlight, every single atom, right? To the smallest atom, we got gazillions of atoms in a flashlight, but all atoms, especially those that participate in the light phenomenon, right? They're already attached to whatever you're illuminating. So if you're pointing the flashlight to the wall, every atom that from your bulb or from the glass or whatever is already connected to the wall. Okay, but you haven't turned the light on yet. Okay, it's turned off, so you don't see anything. You say, okay, I've got the flashlight here, and the wall is dark. You know, you don't. There's nothing in between. Suddenly, you turn the light on. You press a button, right, and suddenly the wall illuminates. Right, suddenly you have an image on the wall. What has happened? According to the rope model, every atom from your bulb to every atom on the wall is already connected, and the ropes are in this direction, right? In this case, right? Sideways, right? But here you're seeing it from the flashlight to the wall, and they're torquing. All of them are torquing, okay? So this is what's happening. That means that now they're in a frequency, they're in a speed, right? They're in a torsion that comes visible to our eyes, because now that signal from the atom on the wall is coming to your eye, which is also connected to that atom on the wall. Before, it was below a frequency that you could not see. Suddenly, you put the flashlight, now that same atom is reflecting, in other words, torquing the rope that's connected to your eye. So now you see it. Why? Because it's within the frequency that allows visible light. Okay, so you have this beam of all these atoms, all these ropes connected. They're all torquing at a given frequency, and that's why we see this light. If you you'll see some pictures out there where that light is shining through a gas, sometimes through air, whatever, and you see the reflection of that light sideways. And it comes to your eye because it's hitting every atom of air or whatever gas is there, and that's what's coming to your eye. That's why you can see the whole beam sideways, because every atom in between is sending you to your eyes through a rope that's connected to your eyes, is sending you that signal, sending you that frequency. And so, yeah, that's essentially it. It's essentially a simple world that Mother Nature has through the ropes, but you have to make that assumption that everything is connected. Every atom is connected to each other.
So we see the light, the illumination, because the ropes spin faster?
Right. What you have is you bring, if you have below a certain range, you have what is infrared or ultraviolet, and you cannot see except within those two ranges. So it's got to be within that frequency for you to be able to see it, you know, for the first time. So when you when you have the flashlight, all the ropes are already connected. You don't see that because it's below the frequency that allows you to see it. You can't touch anything. You can't touch any of the ropes because they're untouchable, unseeable. So you say there's nothing there. But suddenly you turn the light on and you say, oh, magic. Suddenly all this light shines by magic on the wall, and you say, oh, magic, how did this happen? Well, all you did was raise the frequency on each rope to the atoms on the wall, which now are shining they're pumping faster. They're also sending that torsion to your eyes, and that's why you can see the light on the wall.
Okay? Oh, okay.
That's the explanation. It's a relay mechanism, not a bouncing ball mechanism like quantum has.
Okay. So let's assume that all the atoms in the universe, or like the atoms in your room, they just pulsated faster. Would that mean that we could be, if let's just say they pulsated really fast, would that mean that we could see the threads then?
You'll never see the thread because you can't see atoms, let alone the rope or the thread, which are much, much thinner, you know, than
so
an atom.
Small. Okay.
Yeah, we're talking about something extremely thin that's unimaginably thin, but you have to think of it as a very thin thing that connects two atoms, but it's a physical thing that we cannot see or touch, okay? But the only way you're going to see ropes is if you have gazillions of them torquing at a given speed and inducing other atoms to pump, because what they do when the rope torques at a given speed, it forces the atom to pump at a bigger speed. So it's doing its quantum jump. It's going back and forth. The membrane is expanding and contracting, which is called the quantum jump, right? They have a little bead going back and forth. We have the whole balloon expanding and contracting at a given speed, very fast. And what it does, it torque any rope that's connected to that atom and also forces that signal to be relayed to another atom. For example, your eye. Okay, so what we have is a relay. What you have in your room is a bunch of atoms of air, whatever you have in your room, and they're all pumping at a given speed. And you can stimulate them by shining something at them, and suddenly, that atom begins to pump faster and sending the signal at a higher torque to your eye. And now it comes within the visible range. So if you enter a dark room and there's a table there, you don't see it, you turn the flashlight on, and suddenly the table becomes visible to you. How did that magic happen? It happened because every atom of your flashlight is connected to every atom of the table, and every atom of the table is connected to every atom of your eye. So now you're torquing the ropes at a higher frequency that allows the atoms of the table to torque faster and send that relay the signal to your eye. That's what we're seeing.
Okay, got it now. All righty. Well, that was a very good discussion. A lot was discussed, and thanks again, Bill, for being on.